So we are going to talk about the definitions of inner and outer semidirect products. To do that, we're going to start by looking at complements. So we say that two subgroups H and K of a larger group G are complements if HK equals G and H intersect K is the identity. Now when we say HK, what we're referring to is the set of all elements of the form H times K, where H is in the first subgroup and K is in the second subgroup. So if the set of products like this gives us the group and the two subgroups only intersect at the identity, then we say that they are complements. Now let's suppose that we have two subgroups H and K that are complements in G. We're going to consider a specific map, phi, that goes from H cross K, this Cartesian product of sets, to the group G. And the map is going to send H comma K to the element HK. What we want to show is that phi is a bijection. So we can start by showing that phi is an injection. To do that, let's suppose that we have two elements, H1K1 and H2K2, that are equal. We want to show that this means H1 equals H2 and K1 equals K2. In order to do that, let's isolate all of the H's on the left side and all of the K's on the right side. So we're going to multiply by H2 inverse on the left. So we get H2 inverse H1. And then we're going to multiply by K1 inverse on the right. So that gives us over here K2, K1 inverse. Now here's the important thing. On the left side, we have an element of H. And on the right side, we have an element of K. So if these two are equal, then whatever this value is, it has to be in both H and K, meaning it's in H intersect K. But because H and K are complements, H intersect K is just the identity. So the only way this is possible, the only way an element can be in both H and K, is if it's the identity element. Now if we have H2 inverse H1 equals the identity, that means H1 equals H2. And if K2 K1 inverse equals the identity, then K1 equals K2. And from that, we've shown that phi has to be an injection. The only way to get the same product is to start with the same pair of inputs. We also need to show that phi is surjective. And to say that phi is surjective means that it maps onto every single element in the second group G. So if we look at the image of phi, by definition, this is the set of elements that phi maps to. That's going to be given by the set of elements of the form HK, where H is in H and K is in K. But we know that this is the same thing as H times K by definition, and we said at the beginning, if H and K are complements, this has to be the original group G. So the image of phi, the set of outputs that phi gives, is the same as the codomain, and that means that phi is surjective, so we can conclude that it's a bijection. So let's say that we have two subgroups H and K of G, and suppose that we also assume that H is a normal subgroup of G. There's an interesting thing that we can try here. We know that phi is a bijection, and G over here is a group. But this H cross K, we didn't really define as a group. It's just the set of elements that look like H comma K. But maybe there's a way to turn H cross K into a group so that this phi isn't just a bijection, it's an isomorphism. So if we could find a group law on H cross K that makes this an isomorphism, that would be really useful because then we can look at elements of the form H comma K, and that lets us sort of factor out one part we're looking at just H and one part we're looking at just K. So it gives us a way to simplify the larger group. Now for phi to be an isomorphism, it needs to be a bijective homomorphism. But we already showed that if H and K are complements, it has to be a bijection. So all we need to do now is to find a group law that makes phi a homomorphism, and then it will automatically be an isomorphism. That means we need to find a group law such that phi of H1 K1 times H2 K2 is the same thing as phi of H1K1 times phi of H2K2. So this is the rule for homomorphisms, that we're able to split up a product and look at phi of the first thing times phi of the second thing. Now we haven't defined a group law on H cross K yet, which means that we don't know what the product on the left is going to be. But on the right, we know that phi of H comma K is equal to H times K. So we can write that in both of these cases. Phi of H1 K1 is going to be H1 times K1, and similarly this part is going to be H2 times K2. What we want to do now is try to write this element right here in the form H times K for some element in the first subgroup and element in the second subgroup. And we'll see in a second why that's going to be important. But let's see, is there a way for us to write this as H times K? Well, that's the reason that we defined H to be a normal subgroup of G. What that means is that if we write K, H, K inverse, because H is normal, this has to be in the first subgroup H. So notice right here, we have K1, H2, and we don't know exactly what that means. But we do know K1, H2, K1 inverse. This is always going to be in the subgroup H because it's normal. And we can write this product right here, H1, K1, H2, K2. We can write as H1, K1, H2, and then in the middle right here, between H2 and K2, we're going to put K1 inverse K1. And that doesn't change the result of the product because these two are going to cancel out. They're inverses of each other. So we have the same product as before, but now K1, H2, K1 inverse we know is in the group. And so this part is going to be in H, and this part is going to be in K. Now here's why it's important that we can write this as a product of something in H and something in K. The reason is if we look at our map phi, phi of H comma K is equal to H times K. So if we have a product that's of the form H times K, we can write it as phi of the first part, comma, the second part. So right here, this product is equal to phi of the part in H, which is H1, K1, H2, K1 inverse, comma, K1, K2. Because the way we evaluate phi in that case is just to take the product. So we have phi of this product right here has to be equal to phi of this ordered pair. But we know that phi is a bijection. In particular, it's an injection. And the property of an injection is that if we get the same output, we must have started with the same input. The only way for these two evaluations of phi to be equal is if the inputs are equal as well, which means we get H1 comma K1 times H2 comma K2 must be equal to H1 K1 H2 K1 inverse comma K1 K2. And so this immediately gives us the group law for multiplication in H cross K. If we define this to be how we multiply two ordered pairs HK, then we immediately get that phi is going to be a homomorphism, and therefore this is an isomorphism from H cross K to G. Sometimes when people look at this final multiplication rule, it seems like kind of a random rule to use. If we're multiplying H1 K1 and H2 K2, why is there suddenly K1 H2 K1 inverse? Did we just add that in randomly? The answer is no. So we have to remember that when we look at this ordered pair, if you think about reading it from left to right as a product, the point of making the multiplication like this is that K1 inverse K1, if we look at it as a product, is going to cancel out, and we just get H1 K1 H2 K2. So this conjugation part is really just in here so that we can sneak in H1 K1 H2 K2. And because H is a normal subgroup of G, even though we're conjugating by K, which isn't in H, it's still going to stay in H because it's normal. So this is just a way to take a product of H1 K1 H2 K2 and split it up into an ordered pair where the first element is from H and the first element is from K. Now remember that the elements in this group are of the form H, K, but we don't write the group as H cross K because often that's used to talk about the direct product of groups. So in order to show that this multiplication rule is a little bit different from the direct product, we write the group as H times K with this specific times symbol where we have the triangle pointing towards the normal subgroup. And we call this the semidirect product of H and K. And the whole reason that we wanted this multiplication to work out so that it becomes H1K1, H2K2 is so that when we have the map phi that sends H, K to H times K, we want it to be a homomorphism. So we want this product to work out such that if we multiply these two together, we do get H1K1, H2K2. And because we define the group law to make this a homomorphism, we're able to say that the original group G is isomorphic to the semidirect product of H and K. And that's what lets us break down the original group into just looking at the ordered pairs with this group law. Now what we just finished is called the inner semidirect product because we start with a larger group G and we use subgroups to break it down into something smaller. What we're going to do now is something different. Suppose that we have H and K being groups, but these aren't necessarily related to each other at all. They could be completely separate and unrelated groups. What we want to do is we want to find G such that G satisfies all of these conditions. Now in these conditions, I'm using H sub G to refer to a subgroup of G that's isomorphic to the original group H. It might not necessarily look exactly the same, but it needs to behave the same way. In other words, it needs to be isomorphic to the original H. Now the set of conditions that I put here is the same set of conditions that we had for the inner semidirect product. So essentially our goal here is to take two groups and make a new group out of them so that G is isomorphic to the inner semidirect product of H and K in that larger group. So earlier in the video, the conditions we were looking at were, first of all, we wanted H and K to be complements, so they intersect at the identity and they multiply to get G. And we also wanted H and K to be subgroups of G, and in particular we wanted H to be a normal subgroup of G. Now let's think about how we can make a group that satisfies this condition. The first thing that we have to remember is that we don't know anything about H and K as groups, and they don't necessarily need to be related. So if we think about taking an element of H and multiplying it by an element of K, we don't really have any idea of how we would do this. So we can't really just write this by itself. We want to think about some way that we can treat the elements of H and the elements of K as separate. One way that we can do that is to use ordered pairs. So we can say that the set of elements, G, is going to be the set H cross K. So every element in G is going to look like H, K for some H that's in the first subgroup and K that's in the second subgroup. Now we don't necessarily need to worry about multiplying H and K together because we can keep them separate. And if we use these ordered pairs as the elements of our larger group, it also makes it easy for us to find H and K as subgroups of G, because we can say that H is the subgroup H cross the identity element in K, or in other words, it's the set of elements of the form H, E. Now, we want this, H sub G, in our larger group, to work the same way as the original H. It needs to be isomorphic to H. And in order for that to be true, the elements need to multiply the same way. So if we have H1, E times H2, E, this needs to multiply the same way as in the original group. We can just say that the product is H1, H2, E. So that gives us our group law when we're just multiplying elements in H. Similarly, if we want to look at a subgroup isomorphic to K, we can look at the identity element as the first in the pair cross K. And then if we want multiplication to work the same way as in the original group, we can say E comma K1 times E comma K2 multiplies the same way, we get E comma K1 K2. So that gives us multiplication with H comma E and multiplication with E comma K. We've satisfied the condition of K being a subgroup, and also note that we can look at H intersect K, because for an element to be in H, we need that the second thing in the pair is the identity. For an element to be in K, we need that the first thing in the pair is the identity. So to be in H intersect K, both the first and the second elements need to be the identity. And so H intersect K is just going to be the element E comma E. Or in other words, the identity element in our new group. So we've also satisfied the condition that the two subgroups intersect just at the identity. Now let's take a look at the next condition that we want to satisfy. H times K gives us our larger group G. To recap, if we want H times K, this set is the same as the set of elements of the form H comma E, that's our first subgroup, times E comma K. So this is an element from the first subgroup times an element of the second subgroup. Now we want this to equal the entire group G. Remember that the group is given by the set H cross K. So that's the set of elements of the form H comma K. Now if we want these two sets to be equal, there's one easy way that we can do it. We can define multiplication. We can define our group law so that H comma E times E comma K is equal to H comma K. Now if we're looking at two arbitrary groups H and K, we don't necessarily need to define our group law this way. But if we define it this way, it very easily gives us this final condition. So we're going to define that our group law, if we multiply an element of H with an element of K, just puts them together in the ordered pair. And that satisfies this condition automatically. So using this multiplication rule, we get that every single element of the group, which is H comma K, can be written as H comma E times E comma K, and therefore H times K gives us the whole group. So we've defined multiplication in a few specific cases, but now we need to figure out what is multiplication going to look like for two arbitrary elements of our set H cross K. So let's see how that would work. The two elements are going to be H1 comma K1 times H2 comma K2. What we can do now is take these two ordered pairs and expand them out to make it look like the case that we saw with inner semidirect products earlier. We know that we can write H1 K1 as H1 comma E times E comma K1. That's how we defined our group law. And similarly, H2 comma K2 is H2E times E K2. So this looks a lot like what we saw with the inner semidirect product. H1 times K1, H2 times K2 here. Remember that we want H to be a normal subgroup of G, which means that if we conjugate H by an element of K, it's going to stay in H. So we're going to do the exact same thing that we did with the inner semidirect product. We're going to write this as H1E and then E K1, H2E, but then in here we're going to put E K1 inverse and then E K1 to cancel it out. Now when we do that, we get right here K1 H2 K1 inverse. This is conjugating H2 by an element of K. And we want H to be normal, which means this always needs to be of the form H comma E for some other element in H so that it stays in the subgroup. Now we need to figure out what is this conjugation going to look like. Now before we figure out what H is, we first need to look at some properties of conjugation. Remember that in a group, conjugating by a group element is an automorphism. And in fact, it has a special name. When we look at an automorphism that's described by conjugation, it's called an inner automorphism. So we can look at a map, we'll call it psi, that goes from G to the automorphism group of G. And what this is going to do is it's going to take some element G in the group to psi of G. And this is the automorphism map of conjugation. So if we apply psi of G to some specific element X, it's going to give us Gx G inverse. Now what I want to investigate is what is psi of a product, psi of GH. If we apply this to X, by the definition up here, it's going to be GH times X, and then times the inverse of GH. Well, we know in a group, the inverse of GH is given by H inverse G inverse. Notice what happens here. On the inside, right here, Hx H inverse, that's the same thing as psi of H applied to X. It's the conjugation map with H. And we're doing G times this group element times G inverse. This is again the conjugation map. So we can describe the conjugation G times something in here times G inverse as psi of G applied to the inside here, psi of H of X. Notice psi of GH applied to X is the same thing as psi of G applied to psi of H of X. Remember that in the automorphism group, the group law is composition. So when we say psi of G of psi of H, this composition operator is really group multiplication in the automorphism group. So what this is saying is that psi of GH is equal to psi of G times psi of H. In other words, psi is a homomorphism. So if we think about the map that goes from a group to the automorphisms of that group, if we look at all of the group elements together, that map has to be a homomorphism. So let's apply this to the case we're looking at here. We're conjugating an element in H sub G by an element of K sub G. And we know that the conjugation map is going to be an automorphism from the group to itself. But in this case, we also know that H is a normal subgroup, which means that when we apply the automorphism to H, it's going to just send it back to H. So we can look at a more specific automorphism. When we conjugate an element in H sub G, it's actually going to send H sub G to itself, which means we can look at just an automorphism in H sub G. And in fact, we can get even more specific than that, because when we look at an automorphism from H sub G to itself, the elements of H sub G just have the form H comma E. The comma E doesn't really affect the way that an automorphism works, because we know that H sub G is isomorphic to the original group H. So we can describe an automorphism from H sub G to H sub G just by looking at the single group H. So we're looking at an automorphism from H to itself. So if we associate every element of the form E comma K with an automorphism on H, we can describe that using a map psi that goes from K, that second element in the ordered pair, to the automorphism of H that's described by that conjugation. And by the same argument that we saw up here, we know that psi has to be a homomorphism. So what we're saying with this map is that for every element K, psi of K describes the conjugation map, where we conjugate H comma E by E comma K. Therefore, by definition, what we have down here, this H comma E, this is really psi of K applied to H2 in this case, comma E. And in this case, we're also looking at K1. So this psi describes conjugation when we conjugate H by K. It's given by psi sub K1 of H2 comma E. But specifically, this map has to be a homomorphism from K into the automorphism group of H. And now we're able to finish doing this product. The reason is, on the left side, we have H1 comma E times this psi of H2 comma E. So these are both elements of H, and we know how they multiply. We just put them together. So over here, we're going to have h1 times psi k1 of h2. Now, on the right side, we have e comma k1 times e comma k2. We know that that's just going to multiply to get k1, k2. So we have this comma e times e comma k1, k2, and we can multiply those together. We just combine the pair. So our final result is just going to be this pair right here with k1, k2. So when we multiply h1, k1 times h2, k2, the result we get is h1 times psi k1 of h2, comma k1, k2. And when you look at this result, it should make you think back to that inner semidirect product that we had before. This looks just like what we had with the inner case, except instead of k1, h2, k1 inverse, we have this map psi. But really, this map psi is just conjugation in disguise, because what this psi k1 of h2 is describing is the conjugation of h2 by k1, just like in the inner semidirect product case. The reason that we use this notation is that it makes it shorter, and it also lets us talk about what that conjugation has to be. Like we said before, that psi always has to be a homomorphism from k into the aught of h. So starting with two arbitrary groups h and k, if we define a new group where the elements are of the form h comma k, and our group law is given by this multiplication with this map psi, we know that this is going to be a group. And in particular, we have all of the conditions that we saw before. H and k are going to be complements in this larger group, and h is going to be normal in G by that conjugation map that we saw earlier. As a result, if we look at this larger group, hg and kg, those are going to make an inner semidirect product in that larger group. So we write that G is equal to H semidirect product K with a psi down here. The reason that we have this psi is that for two arbitrary groups, we don't necessarily need to have one specific way to conjugate the elements. We said it has to be a homomorphism from K to aught of H, but there might be more than one homomorphism. And when that's true, we can sometimes have different semidirect products that actually give us different non-isomorphic groups. But once we define a specific map psi that describes conjugation by K, we have a unique semidirect product.